Hi everyone. So hopefully you watched the reaction that was in the video of magnesium and hydrochloric acid. And this is a reaction I like to use to demonstrate the concept of limiting reagents or limiting reactants. But first, one of them was a solution. The hydrochloric acid was a solution. So we need to, before we start the calculations for that experiment, we need to know how to handle solutions and get moles from them. And so when we have a solution, it's not, just a solid where you can take the number of grams and get the moles. We need to have a concentration, which tells us how much of that solute, in this case HCl, is in the liquid. So the amount of solute over the volume of the solution. And there's concentration units that use volume of just the solvent, but we don't worry about those this semester. And so concentration is the amount of solute over volume of solution. And we wanted to know then how much HCl we were using. We had 100 milliliters of this HCl solution, but that doesn't really tell us how much HCl is there. And so we have to have a concentration unit. And the one that we use is called molarity. Guessing most of you or many of you are familiar with it. So it's the most commonly used concentration unit. And we use a capital M to represent molarity. It has to be a capital M. And it's just defined as the moles of the solute over the liters of the solution. So like I said, there's some concentration units where we would just have the solvent here, but molarity is moles of solute over liters of solution. And so that's what we're going to use. And so we have this handout for the reaction. And what I wanted to do is just, before we do the calculations, we have to kind of review, go through the observations that we made verbally while we were doing it and figure out what the reaction was. So the first thing is kind of general observations that were the same for all of the flasks. And so we noticed, for instance, that there was a gas produced because the balloon filled up, right? And we noticed that that gas burned or exploded. So that might help us identify what the gas was. And we noticed that the flask got hot and the magnesium was fizzing in that solution, in that liquid, and then it dissolved. I ran out of room, so I'll write it down here. So for all of the balloons, that's what all of the flasks, that was what we noticed. Got hot, gas produced, the gas burned, magnesium was fizzing, and the magnesium dissolved. All right, now what about the balloons themselves? Okay, what about the balloons did we notice? Well, in the first flask with 0.3 grams, this was a smaller balloon, and all of the magnesium was gone. So all of the magnesium was gone and fizzed away and dissolved away. And then in the second one, I don't know if I let it go long enough for you to see this or if you could see it, but for that one, also all the magnesium reacted. All of the magnesium dissolved and reacted. But the balloon was bigger than the first one. And then I know the size of the balloons is kind of hard to see on the video if you're not right there because, of course, the diameter of the balloon, the volume changes much, more as the diameter changes. So it's not like it looked twice as big on the video. But the third and fourth balloons were at least close to twice as big as this second one. And they were about the same size. It's hard to tell exact. If the balloons were a little bit looser so that they filled more easily in the pressure, but those balloons were roughly the same size as each other, had the same volume, and they were bigger than both of the preceding ones, but they were about the same size. And then here's where, I definitely didn't let it run long enough. But if you go back and look at it now, and if I measured it perfectly, um, this third one with 1.21 grams, if you really let that go, and I carefully measured it, all of the magnesium would be gone once that stopped fizzing as well. So once the reaction stops, I think it was pretty close when I went and looked at it. But then the last one where I doubled the amount of magnesium, once it stopped fizzing and stopped reacting, there was lots of magnesium left over. So that's the concept of it. If there's lots of magnesium left over, that means we ran out of hydrochloric acid, right? If all the magnesium is gone, then that means we ran out of magnesium. That's what we mean by eliminating reagent. But we need to do the hard work now of doing the calculations for this. So, before I do that though, I almost forgot with the observations. We've got to write the reaction, don't we? And so this observation that the balloon exploded, does that help us identify the gas? Well, yeah, if you can see, there's hydrogen here. If you think about the Hindenburg, that explosion was hydrogen gas. All right, and so then we just have to write the other product because the hydrogen's coming off of this hydrochloric acid. So we're going to make a compound between the magnesium, which was reacting, and the chloride. So how can we do that? How can we know what that is? Well, when magnesium is in a compound, since it's in group 2, it's always +2. I mean, right here it's 0. It's a neutral atom. But in a compound, it's going to be +2. Chloride's in group 7, it's always -1. So it's going to take 2 of these chlorides to make a compound with 1 magnesium. So that means the formula is MgCl2. And then what's the state of matter there? Well, our observation in these flasks was that there was no solid left. So this is not a solid, this is dissolved in the solution. So we'll put an AQ by the magnesium chloride. All right, so that's the reaction, but now we have to balance it. So let's do the hydrogen, right? So there's 2 hydrogen atoms on the right. We need 2 hydrogen atoms on the left, and we're going to be very careful and not change the formula of any of our substances. We'll only change the coefficient. So that means there's a 2 in front there. 2 hydrogens on the left, 2 hydrogens on the right. Now that means there's 2 chlorines. Oh, look at that. It's all done, right? The reaction's balanced. Okay, so let's go and do the calculations then. So now moles are our currency of chemistry. This reaction means 2 moles of HCl react with 1 mole of magnesium. That's what it means 1 atom of magnesium with 2 formula units of this, but simultaneously it means 1 mole of magnesium with 2 moles of HCl produce 1 mole of hydrogen gas and 1 mole of magnesium chloride. So we can do our calculations with that. So we have to work in moles. That's what the currency of chemistry. All right, so let's do that. Let's calculate the moles of magnesium. How can we calculate moles of magnesium? I need to go back to my plain sheet of paper here and do that calculation. So we've got 0.30 grams of magnesium. And we want to figure out how to get to the number of moles of magnesium. Now I know that most of you know how to do this from the chapter 3 part 1 homework, but I'm going to go through it in a lot of detail because I think there are students struggling, and you can skip over this if you already get it and just get to the end. But the conversion factor between grams and moles is the molar mass. And so when you look at the periodic table, you'll see your box with magnesium on it, and right below it, this number 24.305 with no units on it, right? There's no units on that number. That number is the mass of one atom in AMU, and it's the mass of 1 mole in grams. And so from that, we have 24.305 grams of magnesium is equal to, it's the same amount as 1 mole of magnesium. And that's our conversion factor. This is the exact same thing, same conversion as 12 inches equals 1 foot, right? It's no more difficult than that. And you can, with practice, you can definitely do it. So we can use this to go, if we're given grams, we can calculate moles. If we're given moles, we can calculate grams. Just like in the chapter 3, part 1 homework. All right, so let's do the conversion. The conversion is always start with what you're given. Write that down, 0.30 grams of magnesium. And we want moles, so we'll put that in the numerator. 1 mole of magnesium and 24.305 grams of magnesium. All right, cross that out. And if you would promise me to always include the unit and the identity of the substance, you will be much more successful in doing stoichiometry and chemistry. I know not a lot of people do that, but you will catch mistakes. You want to build in a process for not making mistakes on the stuff that you know. So 0.3 divided by 24.305, and I get 0.0123 moles of magnesium. Okay, so let's just hop back over to here, 0.0123. And then you can go through, you don't need to, but go through and practice the other conversions. And see, I doubled it, tried to measure these as carefully as I could so that it doubled, and we'll fill that in. So 0.025, 0.050, and 0.100 moles. So in these ones, it's just doubled. This one I couldn't measure it out far enough to get it exactly half. All right, so that's the moles of magnesium. What about moles of HCl? So we're given a concentration and a volume. Well, the way I would recommend on that, I'll get a new sheet of paper here, is to always just use the molarity definition. So you can do this in a factor label method, and that's fine. That's the way I would have done it. But what I found from working with students over the years is that it's easier, more consistent when we have a definition, just use the definition. Because solution stoichiometry problems in chapter 4 get really tough for a lot of people. And so instead of trying to figure out how to do it factor label wise, just always write the definition down. We have to know the definition anyway, right? Molarity is moles of solute over liters of solution. And just plug in the numbers you're given and solve the missing number, right? You've got a definition, no problem. So what were those values again? 1 molar, 100 milliliters. So 1.0 molar, write down what identity it is, right? What's the substance? We don't know the moles. That's what we're looking for, X moles of HCl. And then the liters, hopefully you can do that conversion now. That'd be 0.1 liter, so 0.1 times that. So when we solve for the moles of HCl, it's going to be 0.10 moles of HCl. Okay, and so then let's just fill this in. 0.10, 0.10, 0.10, because we kept it the same, right? We had the same amount each time. All right, but now we've got to look back at the reaction. So in doing this calculation, we need to know how much is going to react, right? It's not a one-to-one reaction. So the reaction says we need 2 moles of HCl for every 1 mole of magnesium. So we can't just look at these moles, can we? We have to figure out how many moles of HCl are needed to react all the magnesium. And so a lot of you can look at that then and just say, well, we need twice as much HCl as we do magnesium, right? But we want to build in, because, you know, if it's 3 to 2 and then you forget, we want to build in a process to not make any mistakes. So we're going to start with the number of moles of magnesium that we're given, 0.0123 moles of magnesium. And the reaction tells us 2 moles of HCl for 1 mole of magnesium. So that means 2 moles of HCl are needed for every 1 mole of magnesium that we have. Cross those out, right? And we get 0.0246 moles of HCl that are needed or required to react up all of the magnesium. So let's go ahead and write that in. 0.0246. Okay, so what about these other ones then? Well, you go through the same calculation, right? 0.025, double that. It's going to be, I should know this, shouldn't I? 0.05. And then double that again, it should be 0.10. And then double it again, it should be 0.200. Okay, so that's how many moles are needed to react all the magnesium. Now, let's think about this now. Try not to get confused, because sometimes I'll state it wrong or make a mistake, right? We know from our observations which things we ran out of. And so we can identify the limiting reagent just from the thing that we ran out of. But do our moles, are they consistent with that when we look at it? Well, so let's think this through. We have 0.1 moles of HCl. The moles needed to react all the magnesium is 0.0246. So we got way more HCl than we need, right? So that means we're going to run out of magnesium. So magnesium is the limiting reagent, Lr, and we've got excess HCl. Does that make sense? Hopefully that makes sense. Look at the next one, right? So we've got 0.1 moles of HCl. We need 0.05. So again, we've got twice as much as we need. And is that consistent with what we saw? Yeah, all the magnesium was gone. We can't see that there's HCl left, but all the magnesium reacted. What about this third balloon? Said about all the magnesium was gone as closely as I can measure it, right? And the moles of HCl needed to react are the same number of moles that we actually had. So this is the stoichiometric amount. Stoichiometric, I hate that word, just who knows where that comes from, counting, stoichiometry. It just kind of, it's a big word to confuse chemistry students, right? But it just means we have the exact same amount of each in terms of how they react. So they're going to react completely with each other, and none of either one's going to be left over. So in theory, at least, if I measured it carefully, all the HCl would be gone, and I'd be able to drink that solution. Well, I don't really want to drink magnesium chloride, but anyway, you get the idea. So that's the stoichiometric amount where the moles are just matched to react 100% with no leftovers. And then what's this last one then? Well, we already know from our observations that there's lots of magnesium left over. The magnesium was in excess. Is that actually consistent with the moles? Well, yeah, it is, right? Because we needed 0.2 moles of HCl to react all the magnesium. We only had 0.1. So the HCl is limiting reagent. All right, now, here's the thing. This calculation, I hope, helps you understand the concept of limiting reagents, and seeing the reaction, seeing that some of it reacted up, all gone, and some was left over, and hopefully the balloon thing was kind of fun. It was fun for me anyway. But this is meant to help us with the concept of limiting reagents. But when we actually do the calculations, I'm going to show a different way to do the calculations. So this, you can do it this way, right? And a lot of books will show doing it this way. But I think there's a better way of doing the calculations than this. This can get confusing about which one and how many moles are needed to react with that, and so on and so forth. And so I'm going to show a different way for your homework and then for the test to actually do it. And that'll be in the next examples that I do. All right, thanks everyone.